All right. So, as I said, I wanted to talk a little bit more about temperature and pressure and kind of review what you studied about, for example, the ideal gas law and the different gas laws in IPS, not in detail, just in a little bit, so that you can have a feel as to how that affects weather and wind movement and air movement in the atmosphere and things like that. Uh, so obviously there's going to be different temperature and pressure at different places on Earth. We've already talked about how altitude within the atmosphere changes the temperature with the layers. And we know that pressure is going to be different because pressure is caused by the weight of the air um, around you, right? So as you go higher, there's less weight of the air just because you're further from the surface of the Earth. Also, a lot of the air is below you instead of above you, so it's not pressing down on you. Uh, so there's going to be a lot of variations in these quantities in different places within the atmosphere. Worth noting is this kind of definition of temperature as a average kinetic energy of the particles in a material. So I've talked about before, temperature stops being meaningful when there's not a lot of particles, when there's just not a lot of material. That's because it's an average here. So you kind of get close to a divide by zero, situation when you have very few particles. So, if you've got 5 atoms and they all have huge kinetic energy, that appears to be a very high temperature. That's why we would say the thermosphere has a really high temperature at parts of it. But that doesn't really give you the same environment as you would being in Death Valley on the surface of the Earth, right? Which would have a apparently lower temperature, but is sweltering and you have trouble exchanging heat and things like that. Uh, because there's a whole lot of particles with a moderately high kinetic energy. Uh, so again, average kinetic energy or average energy is kind of a measure of temperature. And you can actually get that from the ideal gas law if you want to. So if you remember PV equals nRT, uh, and you had P times V, if I just tell you that that's energy, pressure times volume, then energy equals or is proportional to by the constant R N times T. N is the amount of a material, T is the temperature. So if you have P over V, or P times V, excuse me, which is energy over N, so we rearrange it, PV over N equals RT, then temperature is proportional to PV over N by some constant R. Uh, so PV over N is energy per, or divided by means per uh, atom is temperature. Again, measurement of average energy or the energy per atom of the particles. So that works out from PV equals nRT also. Pressure, again, it's the measurement of the amount of force exerted on a surface, so meaning force per unit area. We talked about this in the context of stress in a material in earthquakes and things like that. So stress in a material is a pressure, it is a force per area exerted by the weight of the atmosphere above the surface. So, if you've got something sitting on you, if you've got a cat or a dog sitting on your chest, they're applying a weight to you. If they're standing on your chest, it's going to hurt more because they have a smaller area, just their little paws, right? And then the entire weight is pushed down on those forepaws. If they lie down, it's more comfortable because they are spreading their weight over a larger area. There's less pressure, even though there's the same force. We measure pressure in various units. Pascals is the SI. Bars is also SI. Atmospheres is a common one, so that's a unit of how many times stronger or weaker it is than the weight of Earth's atmosphere at sea level. There's also things like millimeters of mercury or inches of mercury or millimeters or inches of water, which is referring to the weight of a column of mercury. And again, this doesn't matter how big this column is, right? Because if it's very wide, there's more area, so the pressure is still the same. Notably, millimeters of mercury, mmHg, is also called torr sometimes. You will probably hear me say torr aloud, even though I've talked to the IPS teachers and nobody uses that in IPS. Just know that that's the same thing as millimeters of mercury. TORR is what I'm saying with torr. But I mean, my favorite unit is either kilopascals or megapascals in the case of stresses, or atmospheres, because atmospheres is very easy to talk about, right? It's just how many times stronger is it than Earth's atmosphere at sea level. I would go through this concept check on your own to see if it makes sense to you, how to calculate the mass of air in the room. We know that we can find a density, and if we have a volume, that's the room of I-11, then you can calculate the mass. You can convert mass to weight. Well, this doesn't even involve converting mass to weight, but you can convert kilograms to pounds mass, not the same as pounds force, and you get that the weight or the mass of air in I-11 is something around 800 something pounds. So if you think about the mass of air in a column that goes straight above your head all the way to the top of the atmosphere, you can imagine that is a huge amount of weight. And it works out to about 14 point something, 14.4 I think, pounds per square inch. So if you take a square inch of your tissue, the air is pushing in on that with 14 pounds of force. And of course, if that went away, if that disappeared all of a sudden, your body would just rupture because it's so used to having all of that force pressed against it that if you remove the force, of course, the mechanical aspects of the body just start to fail. You start to get tearing and things like that. So this is just kind of showing these columns of air and pointing out that at a higher elevation you have a shorter column of air, and so therefore you're going to have less pressure. And this change happens fastest at around sea level because that's where the air is densest, right? So if this column went up way to the top of the atmosphere, let's pretend like this is the top of the atmosphere at the top of the page here, or the top of the monitor. If we had, you know, a mile thickness of air up here, calm down cats, then that mile thickness is going to have a lot less air in it than a mile thickness at sea level, because as we mentioned, 90% of the atmosphere's mass is in the troposphere, which is only a thin layer. So it's kind of like it's densest down at the bottom, which makes sense because it's all collapsing down towards the Earth. And so any differences in elevation here towards sea level are going to make the biggest changes in pressure compared to changes in elevation up here in the stratosphere, mesosphere, thermosphere, and exosphere. This asks, let's go back. What if there was no atmospheric pressure on the oceans? So just like if we had no atmospheric pressure on us, our body would rupture. The oceans could not remain liquid if there was no atmosphere. Basically, the water would all boil into water vapor, basically kind of in an attempt to create a water vapor atmosphere. It's only because of the pressure of the nitrogen gas and the oxygen gas on the water that the water can remain liquid. Without the nitrogen gas and oxygen gas, our water would all be water vapor. We've seen this curve before with the temperature and with altitude, ozone layer right around here, right? So it starts to warm up, especially above it, but also a little bit below it. And then we have the mesopause, the coldest place on Earth, heating up as there's more interaction with solar radiation at the upper atmosphere, and then exosphere way up here. Pressure, on the other hand, is uniformly decreasing as we get higher. There's none of this ozone layer related blip here, or solar radiation related increase in the thermosphere. As we increase altitude, there's just going to be a larger and, less and less air sitting on top of a given point, and so therefore the pressure is going to go down and down. This is millibars. The relationship, just for an ideal gas law reminder, if you increase pressure, you squeeze harder, right, you're going to increase the temperature. PV equals nRT. P and T are on opposite sides, so they both have to go up together. If you increase pressure, then you can decrease volume, which will increase the density, right? It'll pack these into a smaller volume. Smaller volume, density equals m over v. So velocity goes down, that means density goes up. Temperature goes up, then the density goes down because it swells to fill a larger volume. And these are depending on, kind of the third thing being constant. So if pressure goes up and volume is constant or density is constant, then the temperature goes up. If pressure goes up and temperature is constant, then density is going to go up or volume goes down. If temperature goes up and pressure is kept constant, then density goes down or volume goes up. That's basically saying that that's what we're seeing here. The density, no, this is going to be, yeah, temperature goes up here. Pressure, I'm assuming that's like French or something. I don't know what's up with the pressure. Is going up. So that's actually this one, because here the density has been forced to change. In fact, this doesn't make sense whatsoever. Ignore this diagram. These are all correct. Ignore this. I have no idea what this diagram is even supposed to say. Thermal inversions or temperature inversions. This is one of your discussion questions, or it relates to it. This is specifically a tropospheric kind of phenomenon when we talk about it. And we know that in the troposphere, usually the ground is warmer because it's absorbing all the solar radiation, and then the higher troposphere is colder because it's further away from that warm ground. Since hot air rises, the warm air at the surface will go up into the higher troposphere, and there will be a good mixing. If there's a layer of, for example, hot smoke here above the cooler surface air here, that mixing will not happen, basically because this air here at the bottom is cooler than this air up here, so it will not rise up. It has no impetus, no force on it to push it upwards, and therefore you get no mixing, and especially if this is caused by something like smoke or an air pollutant in general of any kind, that means this pollution is not mixing very well, and it has some serious effects, and I encourage you to look that up in independent resources, as I said in the discussion questions, because there's a lot of important stuff, both historical events and laws and all kinds of things that have to do with kind of the generation of smog because of thermal inversions. Notably, another thing that's caused by air temperature and pressure is any kind of wind or air movement. Basic idea is here, if we have, for example, cold air, it is on its way down, it's dense, it has high density, therefore high pressure, right? And then we've got something with high temperature, therefore it's got a, well, it's a high temperature, but it's rising, and because it's rising, it's creating kind of a vacuum here, so let's not look at that one. It creates a vacuum underneath it. It's also low density here, high temperature, low density. And therefore we have less pressure here. This air is coming down, it needs someplace to go, this air is moving up, it's creating this vacuum beneath it, and so the air will flow from high pressure to low pressure, generally, therefore, from the colder regions or the areas where there's cold air to areas where there is warm air. And because there is unequal heating and cooling of Earth's surface, we talked about that plenty in the first quarter, right, about the incoming angle of sunlight and things like that. There's going to be movement of air generally towards the equator and away from the poles. And we also know, based on our previous studies, that there's going to be a Coriolis effect involved in there somewhere, right? When we hear movement of air in a latitudinal direction, we know there will also therefore be a deflection in a longitudinal direction because of the Coriolis effect. And because of laminar flow laws, the wind tends to be slowed by surface friction. So it's faster, kind of a little bit above the surface, and slower near the surface. It's also what causes things to blow in the wind, right? That's because they are catching the wind. They're causing drag force and surface friction and being pulled along with it. They're taking some of that energy. I'm going to talk briefly about humidity because I think it's important, although it didn't really play a role in your discussion questions so far. There's relative humidity. It's the fraction of kind of the total saturation of water in the atmosphere that it currently is experiencing. So if you've got a dry area, maybe you've got a dry hot area like Death Valley, that example, right? You have not very much water in the air compared to the amount of water that it could hold because it's very hot, it's not very dense. There's plenty of room for water vapor gas in the air, but there's not a lot of water vapor there just because there's not a lot of water to evaporate. On the other hand, if you've got a very cold place like Antarctica, but there's lots of ocean nearby that's kicking up humidity, maybe it's got a pretty high relative humidity, even though there's not a lot of water in the air because it's just so cold it can't hold very much. And then there's places like the tropics where it's got a high relative humidity and there is a lot of water in the air because it's high temperature, so it can hold a lot, and it's by the ocean, so there's a high availability of evaporated water. So relative humidity is a fraction compared to how much water the air could hold. And if there's 100%, that means it's raining because that means that you have maxed out the saturation of the atmosphere, and the water starts to have to precipitate or condense. Dew point is another way to kind of reflect that same thing. It's talking about the temperature. So relative humidity is a fraction of the saturation level, right? Dew point is a temperature, and it's the temperature at which, if we kept the same amount of water in the air, let's say there is a density of 2% water vapor in the air right now, at what temperature would we have to drop our air to make it 100% humidified? At what point would dew start to form if we cooled down the air in the room? So here's a good way of showing relative humidity. So if we have a certain amount of water vapor in the air, and that is equal to the amount that the air can hold, that's 100% relative humidity. At that point, any extra water is going to form as precipitation. If we heat up that air, then it can hold more water vapor, but that doesn't necessarily mean we're getting more water in there. So the relative humidity appears to be less, and then as you heat up that air even more, the relative humidity seems to be even less. Dew point, again, is at what point do you have to cool down the atmosphere in order to create dew, which is why you have condensation on cold. You guys know how condensation works. I don't need to talk about that. But the dew point is the temperature at which condensation will occur given the amount of water in the air. Just because this is worth remembering, I don't know exactly where it's going to come up necessarily. At least in our kind of more abstracted discussions online. But latent heat, it's talking about there's an additional amount of energy required to change states. So like when you have ice water, the ice, you would have to, even though the ice is 0 degrees and the water is 0 degrees, it still requires a lot of energy to melt the ice within that, even if you're not raising it from 0 degrees, right? Ice at 0 degrees has less energy than water at 0 degrees, and water vapor at 100 degrees, or water, steam at 100 degrees has a lot more energy than water at boiling, basically than boiling water. If you put your hand over boiling water, and there's a fast enough movement of steam, that's going to actually be worse than putting your hand into the boiling water. So if you have to choose between boiling water and this is what a physics teacher said to me once. It's the weirdest thing. If somebody ever has a gun to your head and says you have to choose between putting your hand in boiling water or in this in front of this steam pipe, you want to pick the boiling water. It's going to be a lot less damaging than high pressure, high speed steam. Just because the steam has all of that latent heat also. Adiabatic just means, that's a word that means slow. So if we talk about adiabatic heating or adiabatic cooling, it generally is talking about this process that is very slow, that does not involve direct heating or cooling. It's actually caused by the change in density of the air. So remember that temperature is kind of the average energy of something. So as we have fewer particles with the same energy, because it's becoming less dense as it expands, so here we're going up. If something is rising, it's expanding. We're getting fewer particles. That is going to be a cooling, because there's less total energy in that volume. Does that make sense? In any case, there's less total energy in a volume, and so it appears to be cooler, right? Just because you're not getting as many collisions as you otherwise would. Whereas when something compresses over time, say it's sinking, it is going to warm up as a result. So you're getting more particles with the same energy, therefore more collisions in a unit of time if you had like a temperature sensor following this air down. And notice that this is the opposite of what air wants to do. Cool air wants to sink, and warm air wants to rise. So this will create a cycling. As something adiabatically heats up towards the ground, it's then warmer, so it wants to go back up. And then as something is cooling adiabatically, it therefore wants to start sinking because it is colder. Now this depends on the density being able to freely change, because remember that this is caused by an increasing density, and hot air usually wants to expand further and decrease its density, so that's another way to look at this. But this is kind of important when we talk about how, or when the book talks about at least how kind of different clouds form, and about how air moves in storms. I wouldn't, at least right now, don't get too bogged down in trying to understand the adiabatic processes. We will come back to that in meteorology, definitely. Let's see, do we want to talk about, yeah, let's talk about the different ways that air lifts. So air obviously can lift because of density changes, kind of like how we talked about water currents in the oceans, right? There's going to be density currents, and there's going to be surface currents. So the same kind of thing happens with air. There's going to be convective lifting, which is kind of like a density current. It's caused by the change in density. And then there's going to be kind of collisions of things, orographic lifting and convergence, that are kind of more like the surface effects. in the oceans. So orographic lifting, oro, it means mountains. Orogenic was mountain building. So this is just talking about how when air passes over a mountain, it is going to rise up higher. Since it's rising air, it expands and cools, so it becomes cooler. It therefore will, if you want to think ahead to precipitation here, it will have a lower dew point, or excuse me, not a lower dew point, a lower saturation point for air, and so therefore a higher relative humidity, so it is going to cause there to be precipitation. It may cross the air's dew point, is what I was trying to say, and therefore cause condensation and precipitation, which is, of course, what leads to this rain shadow that we have talked about multiple times throughout the year, where there's a raining on this side and none on the other. This is on Hawaii's Big Island. Very clear ridge here with a rain shadow and a dry side. And convergence is just where basically two currents collide, and since they have nowhere to go, they go up. They are forced upwards. And when something is forced upwards, you know for sure that there's going to be precipitation because it, again, undergoes that adiabatic cooling. It cools past the dew point and generates condensation. This also can cause cyclones in this case and anticyclones in this case, where the rising air kind of sucks things up, right, like a tornado. And here the air is being pushed down. This can also happen in a thermal inversion, anticyclones. So it's worth thinking about how those work. Again, this is high pressure because it's basically being pressed down on here. Low pressure because it's basically a vacuum as air lifts up. And then I would ask you to start looking in chapter 12 about kind of the different cells, Hadley cells, Ferrel cells, polar cells, and how the Coriolis effect deflects things east-west, whereas these kind of pressure convective cells and convergence push things up-down and towards the equator, and then in the Ferrel cells away from the equator also, just to spoil a little bit, but in polar and Hadley cells towards the equator. So have a look at all of these things in chapter 12. It's very important. It is part of the answer to your second discussion question, and we're going to skip clouds, I think, just because that always bothers me a little bit. I would take a note of what a raindrop's shape actually is. That's like a worthwhile slide to look at. And then we'll continue on the next slideshow, which you already have access to. Probably next week. All right, thank you very much. Look over this. There will be a quiz on this material. Again, open everything on Tuesday, and use the discussions as a way to kind of solidify some of this information. I know that some of it can get complicated, but as long as you understand things like relative humidity and dew point, you should be fine. All right, I will be in touch in the Discord.